This video is about cell potential. By the end of this video, you should be able to calculate cell potential from standard reduction potentials. You should understand the relationship between cell potential and free energy. Cell potential, which is abbreviated with a cursive letter E, is the pull or the driving force on the electrons in a voltaic cell. It's often referred to as the voltage of the cell. So a 9-volt battery would have a cell potential of 9. In order to calculate the cell potential for a voltaic cell, we need to consider the standard reduction potentials of the anode and the cathode. The standard reduction potential, which is abbreviated cursive E with a degrees symbol for standard, is a measure of a metal's ability to gain electrons, or in other words, a measure of a metal's ability to get reduced. The cell potential for a voltaic cell is equal to the sum of the oxidation and reduction potentials of the anode and the cathode, as shown here. Elements that tend to lose electrons more easily will have lower reduction potentials and are said to be more reactive. The species with the higher reduction potential will be more likely to be reduced, therefore it will act as the cathode in the voltaic cell. The other electrode with the lower reduction potential will be less likely to be reduced, therefore it will act as the anode. Here's a table of standard reduction potentials. You'll always be given these values along with the equation, so there's nothing here to memorize. However, you should be familiar with what these tables look like. Some important things to note about the reduction potential table. First, reduction potentials describe the likelihood or the potential for a metal to be reduced. As we said before, higher reduction potentials mean more likely to be reduced, therefore these metals will act as cathodes more often. So the metal that's higher up on the reduction potential table will be more likely to act as the cathode than the metal that is lower down. Since all of the half reactions in the reduction potential table are written as reductions, we need to reverse the oxidation half reaction, therefore changing the sign on the voltage. For instance, if we determine that manganese is oxidized rather than reduced, we need to reverse the reduction reaction to make it into an oxidation reaction. Likewise, if the reduction potential was negative 1.18, its oxidation potential will be positive 1.18. Finally, when a half reaction is multiplied by an integer, the voltage does not change. This is one of the only non-stoichiometric relationships we'll look at in this class. So to summarize, elements high on the reduction potential table will have high reduction potentials. Therefore, they are the easiest metals to reduce and will act as cathodes more often. Elements at the bottom of the reduction potential table has very low reduction potentials. Therefore, they're much more likely to be oxidized and will most likely act as anodes in a voltaic cell. Let's consider this example together. In order to calculate the voltage of this cell, we first need to determine which metal is being oxidized and which metal is being reduced. Since zinc has a lower reduction potential than copper, it will be oxidized rather than reduced. Therefore, we need to reverse the zinc reaction, and in so doing, reverse the sign on its voltage. Now we can add our two potentials together. Our zinc plus our copper gives us a cell voltage of 1.10 for a standard zinc-copper cell. Here's an example to try on your own. Pause the video here. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. In this case, aluminum is the anode. Therefore, the aluminum reduction potential reaction and sign must be changed. Now let's consider cell potential in terms of delta G and spontaneity. Consider the two reactions shown here. Since they're the reverse of one another, they can't both be spontaneous. One will be spontaneous and one will be non-spontaneous. Since we know that zinc has a lower reduction potential, it will be spontaneously oxidized when placed with copper, which will be spontaneously reduced. Therefore, only the top reaction will be spontaneous. The reverse will be non-spontaneous. Energy will have to be put into the system continuously to allow this reaction to occur. This adds something new to our list of things we know about spontaneous processes. As we've discussed, a spontaneous process will always have a negative delta G. Likewise, it will always have a positive cell voltage or cell potential. It will also have an equilibrium constant greater than or equal to 1. Since delta G then is directly related to the amount of useful work that a cell can perform, we can relate these values using the equation shown here. In this case, N refers to moles of electrons and F to Faraday's constant. Faraday's constant is 96,500, which is given on your reference table. E standard here is our standard cell potential. Recall that delta G is also equal to negative RT ln K, the gas constant times the Kelvin temperature times the natural log of the equilibrium constant. Therefore, we're able to relate all of these values to one another. You can calculate any of these values when given the others, which is very valuable. But more importantly, you should note that based on this equation, delta G is proportional to the negative of the cell potential. Therefore, as the cell potential increases, delta G becomes more negative, meaning the process becomes more thermodynamically favored. That brings us to the end of this video. Let's review our goals. First, we learned to calculate cell potential from standard reduction potentials. Then we looked at the relationship between cell potential and free energy.